In the episode of series, we're going to make another breakthrough to make our robot grab an object with its arms using VLA policies as the tools of an LLM agent. Our robot will decide when to activate its arms and manipulate objects. There is something no one did before us, as far as I know. But do not get scared, it will be not so complicated as it sounds. My name is Grigory, and through that series of videos we want to enable our XLeRobot to be able to fully autonomously clean your house or make you a tea without any human help and presence. In previous video we made an LLM agent to control the movement of our robot, and in this one we want to activate the arm manipulation, combine both manipulation and movement, and try to make a robot to do a real office task, to grab documents from the table and transport them to you. Can advanced VLA policy run locally on the Raspberry Pi? How AI can use another AI? And why train a robot to grab documents? You need first to train a human to grab documents. Well, the problem with making our arms work is that the controlling arms is just much more complicated than controlling wheels. With wheels, our agent just gives a simple command, go forward, and our wheels are rotating. In every arm, however, we have 6 different servos, 6 different joints to control, and it's just impossible to control all of them by LLM. Solution could be a VLAs, a Vision Action Language Policies, that are specially designed to control robots, especially robot arms. To make such policy work, we first of all need to record a dataset of containing many episodes where we demonstrate into the policy how to grab that cup by our manual operation. And then we need to train our VLA policy on such dataset. That's the easy part. But well, problem is that we need somehow to connect our LLM agent and VLA policies. Idea we have is to make VLA policies to be tools of our LLM agent, so he can activate the policies whenever he wants. But will it actually work? No one did it before that way, as far as I know. But for now, let's start with the dataset record. This is the XLeRobot teleoperation. The problem we met here is that XLeRobot at that point of time haven't had any way to record a dataset during teleoperation. That's why we needed to create our own script that records all the joints position and camera data during the VR teleoperation. 2 hours of fighting with dataset problems. Hopefully, with AI help, I managed to solve them, and now we can record our datasets. I'm so happy. I finally managed to create the dataset recorder script. Now you can see that episodes are saved. Let's smile for our robot. Okay, let's save it. Our dataset been saved and loaded in the hub now. It's on the hub, let's see. And we can see our dataset. And then, using the VR goggles and our script, we need to record a ton of different episodes showing the robot how to grab a cup properly. VR teleoperation is not so easy. Oh no. Okay, so finally we can do our VR teleoperation. Our robot can grab cup from the table and put it inside of his own bag. That's Konrad teleoperate on our robot. Grab the cup, Konrad, grab the cup.
Management is important thing.
Yes, we just destroyed one of our cameras occasionally because our cable been connected, yes, too short, too tight, and it been yanked from the camera. We recorded episode after episode. It's a very tedious job, but with every episode recorded, you as a human operator became better at it, became more accurate in grabbing the cup, became quicker. So in the first day of our dataset recording, we in 3 hours recorded about clean 50 episodes. For our dataset. It's bare minimum. I think we need at least 100 to make our policy for one arm somehow work and bring that cup. So we will finish for today, and tomorrow we'll continue recording our dataset and we'll go to train our model. Last one, go! Up, forward, Forward. Forward now, forward. Okay, grab it. Grab it. Yes. We did it. Now we have recorded our datasets, and what we're doing now is the probably most tedious part of it. We just manually looking through all the recordings we did and checking if the recordings are good or not, if the robot actually grabs the cup and puts it into his basket. So we're removing the episodes that does not record it properly, and after that we're merging all the datasets and running the training of our ACT and SmolVLA models. We finally have our dataset collected and polished, and now we can run training of our policy. Training is running! I tried to explain the process of training your VLA policy as truthfully as I could, but if you still have questions about how to train your robot, feel free to ask them in the comments. And finally we have our model trained and ready to test. Will it go into grab a cup? Will it move arm at all? The policy is not catch a cup for now, but the fact it already moved a robot arm is the big success by itself. Our policy is able to control all its joints and even makes a moves that's almost similar to good moves to grab that cup. So now all we need to do to investigate why it not grabbing that cup yet. What we want to do now is to connect the RoboCrew library and our policy to make a robot to activate such policy through as its tool. So our LLM agent will use VLA policy as a tool. So I just created a code that runs the client policy inference on our XLeRobot. That policy will move our arms. It works that way. We have just initialization of our script with the policy name, policy type, some additional configurations for cameras, and also we providing the IP address of our server where our policy will run. So in fact, in the robot we will have only client that executes the policy, but all the complicated calculations will be on the side of our server, somewhere else on powerful machine. Let's try if it works. For sure with first time it will not work, but we will constantly, iteratively improve it. This is actually the core moment of our entire experiment. Using a tool, our agent is able to activate a VLA policy in every moment he wants. If it's close to the cup, it just calls the grab a cup tool and it should grab it. But well, the story will be too perfect to be true if we will not meet any problems again. Trying to make our robot grab a cup. Even if it's not a cup he's been trained for. But what we have another error. Whoa. And it's error related to not finding cameras properly. We constantly having that error that our arms cannot see a camera. My theory now is that probably it's because the AI agent inside of the robot already uses that cameras, and that's why the arm itself cannot find the cameras because they're busy already. What to do? To check if my suspicion is right, we need to separate the VLA tool from the agent. So we create a test script that just calls a tool and does nothing more. We'll create now a new file with our tool to grab a cup to activate an arm, and in that separate file without an agent we do a separation. We'll try to make that arm activation, and we will see if the reason is the problem is here because of that cameras are busy. It's making calculation actions. Whoa! He moves! Whoa, you see that? Ooh. Amazing! We managed to activate our policy on separate script. We activated our policy client from the Python level, and all we need to do now is to somehow solve that problem with simultaneous using of camera by agent and VLA policy, and add that policy as a tool to our agent. My theory confirmed. Our camera cannot be used by the agent and VLA policy simultaneously. So we need to release the camera from the agent first before activating a VLA. It's an agent who activates VLA when sees the cup.
Oh.
See that? He moved his arm. Obviously he will not grab this cup, but he will at least try to do it. Oh. See that? Oh. So sweet. Grab that cup. Oh.
he tries to grab it. But what's most interesting, if after that grab he will not abort all the actions and just get into the bugs, what we want to do is to enable him to grab the cup and do some next actions after it. Woo! Wow, he did! So actually what we see now is that he made some VLA action and after that not get broken but just started to do next actions as turning right.
When VLA started to work, we need to make it work good. Locally, on the Raspberry Pi, we can run on the lightweight policy called ACT. A very simple one. For all different, more complicated policies, our Raspberry Pi just have too small computation power. Let's do something with it.
Finally it seems to work in that tool to manipulate ARM inside of the agent work, and now we want to do it to work remotely, to make our robot be connect to remote policy in some powerful server with GPU and just execute policy on the robot but calculate the policy somewhere on the powerful server. As you can see, we now have a remote server somewhere far away in my remote powerful computer in other city totally, which controls that ARM here now in totally different place.
At least we thought the problem solved. Ngrok stopped work for us later, but even later we solved the problem again with a tail scale. And now it's time to record more datasets and do more tests. We resigned from the task of grabbing a cup by our robot because the room when we tried to do it just had too bad internet connection. So we switched location and switched to another task. We want our robot to grab a notebook from a table and then give it to human. As we use only single arm for now, we choose the much simpler approach to dataset recording. Instead of using VR, which is just complicated, we use so-called leader arm and another robot arm designed specially for remote teleoperation.
Another day of our dataset recordings. We recorded another batch of another 70 episodes, so we want to have 200 episodes in total. We collected some episodes of our dataset, but unfortunately part of the episodes been just destroyed because of some technical problems. Our arms been disconnected during the dataset recording, so in fact we need to record much longer than we intended initially. After all, we managed to record 200 episodes and now we run our training process. We're training the SmolVLA model in our dataset and it looks like this. We already have 7,000 of steps from 120,000 we want to do, and we just need to be patient until it will be done.
We trained an ACT and SmolVLA policy on new, properly merged dataset. Will the policies be able to grab a notebook this time, or it fail like previously?
Trying to inference our ACT policy. Wow! He did it! He did it!
Teraz laptopa podniesie.
This is called generalization.
At that moment we met a problem with Ngrok, a software intended to make a remote connection with the policy server. It just stopped working, so we'll try to run SmolVLA locally on Raspberry. It turns out that SmolVLA is also able to pick a notebook, but because of small computation power of Raspberry Pi, it makes a single move per 3 minutes.
Oh yes.
Dobrze, he did it!
Now let's create a model for another robot task, a given notebook to the human.
Before training a robot to pick up a notebook, we need to train people to pick up a notebook.
In fact, robot teleoperation is not so easy task as it seems to be. We made a lot of tries and errors trying to grab or give the notebook, but after doing another and another 10 of episodes, we finally get better and better in the task.
We have a problem. Our Raspberry Pi constantly get disabled and shut down during our dataset recording, and problem is that it's very hot. We have no radiators here, unfortunately. For now, we just recorded our datasets for like 10 or 20 episodes. We shutting down a Raspberry Pi to allow it get cold, recording them again, another 10 or 20. This is a single way we can do our recording.
We recorded around 100 good episodes in few tries. So now we need to filter the bad episodes and merge all the episodes together in single dataset.
Yesterday I sticked our recorded dataset together and removed unnecessary episodes, because every few sub datasets that I tried to glue together, our Raspberry Pi been shut down by itself because it's been overheated. So what we do now, we're trying to add some radiators here and ventilators to add here more air circulation and make our processor just more cool.
And now let's test the model recorded on our new dataset. He almost did it! Pardon!
What I'm doing, I'm creating a tools in the RoboCrew, enabling robot to grab a notebook from the table or to give a notebook to a human.
And there is a moment when we have all the pieces together. Our robot can move, can grab a notebook, can even give it to human sometimes, but can actually connect all the pieces together in the sequence that makes sense.
Now our task is to make a robot to grab a notebook from the table and put that notebook, that one, here, give that notebook to human. So we'll see how that robot will perform, if he will be able to activate one tool to go to notebook, activate a tool to grab it, go to human, and activate tool to give it to human. Complicated task. Probably it will not work from the first time, but we are full of hope. It seems our robot wants to move a hand, but he did not get exactly close to the notebook. I'm interested if it's a question of prompting or not. Okay, our robot thinks that he grabbed a notebook, and now he goes to human and wants to give that notebook to a human.
Our agent is intelligent enough to find a notebook, but it's not precise enough to approach to the position from which it's able to grab it. For example, here robot tries to grab notebook too early, when it's just too far.
Wtedy działa.
Robot doing a lot of tries to grab the notebook, but all of them are just unsuccessful. While moving and grabbing in separate are working, we cannot merge it together reliably.
We have another problem we can't solve now. Our robot unfortunately is able to grab a notebook when he is placed in the exact position he's been trained in, but when he needs to move itself with own wheels to the notebook and then grab it, he always places in some different position than positions we trained him in, and unfortunately in that quite different but very similar position, it's already not works. Robot attacks people. Robot attacks people. Oh, he going to you to give you a notebook.
And finally, that moment when our robot approached a notebook and successfully grabbed it happened. See how this time he perfectly approaches and grabs. Later have a notebook robot gone to explore for humans, completely opposite direction. Then return, but stuck in the furniture. Definitely need to improve his navigation abilities in next video, but approaching and grabbing part I can finally mark as passed. What about the robot-human interaction? Can our robot have while having a notebook on his board to approach a human and give it to a human? But before we'll go to the final experiments, there is a small, and maybe not small, gift I have for you. We again open source all the code we have written during that video. The first link in the description is the RoboCrew library, the project that contains all the code we have written during all the series of videos, including all the navigation, manipulation, and other agentic things our robot can do. You can just install it with pip and run one of the few examples on your robot to make your robot move and use VLA policies by itself. At the beginning, our robot wasn't perhaps perfect.
Oh no, he attacked me.
Let's give him one more try. He tries to approach. Yes, he did it! He gave a notebook to me.
Amazing! He gave me a notebook. Very good, very good.
We managed to make a robot move and grab or give a notebook in one single run, which is the first step to the generalization, the ability of a robot to do a bunch of different tasks without a pre-training for them. Yes, I know, his navigation is totally not precise and his arm manipulation has glitches and just far away from perfect performance, but there's all the things we're going to improve in the next video. But meanwhile, if the next video maybe is not available yet and you're interested in the VLA policies, I recommend you to check out one of my previous videos when I have a deep dive into the VLA policies and testing few of them across different parameters, checking their performance and comparing, trying to find which is the best. And that's all from my side. Let me know in the comments what do you want to see in the next videos. I'm really interested in your feedback. I not promise that I for sure record the video according to your proposition, but I for sure read your comment, think about it and answer. And as you watch till the end of the video, thank you for that. It very helps that small channel to grow. Also, I will really appreciate if you leave a like and subscribe to the channel. That will again help the channel develop even more. And also will appreciate if you leave a star on the RoboCrew GitHub to motivate us to produce even more cool robotic control algorithms. Thank you and bye.